Good day everyone. We have an interesting exercise here where the cylinder and the piston are shown containing what we could assume as an ideal gas at pressure of 150 kilopascal and a temperature of 400 degrees Celsius. What we know that we have cooled the system until we arrived at a temperature at 20 degrees Celsius. The question says, is the piston resting on the stops in its final state, and what is the pressure in the cylinder? Now we need to find out whether this piston is resting here or not. How are we going to tell if this is resting or not? It's important just to review some basics in order to understand the pressure relation with the volume in a piston-cylinder arrangement. Previously we have discussed that if we have a cylinder piston, and it doesn't matter what medium we have, whether it's an ideal gas or vapor, there is a minimum pressure required in order for the piston to be balanced. And you can do a simple free body diagram for any piston showing the atmospheric pressure relation and the force due to the weight of the piston and the force as a result of the pressure inside the piston. As long as this one balances the other two, we will have a free floating piston. So once we arrive at the pressure that will allow us to lift off the piston, then the piston will actually move up or down, depends on the scenario. So if we add heat, the piston is going to maintain a constant pressure. However, the volume is going to expand or increase. Now the reason for this, or the logic behind it, that assume that the pressure to equilibrate the piston is 100 kilopascal, let's assume. As the pressure increases due to the temperature, suppose that it reaches a 101 kilopascal. Then this extra pressure is going to lift the piston up, and as a result, pressure is going to slightly drop back to 100 kilopascal, maintaining equilibrium, and the process continues as such. This means that the pressure is going to stay the same during expansion. Now the same thing happens during losing heat to the outside environment. When we are losing heat, the pressure is about to drop. However, once this happens, the piston goes down a little bit in a minute change in the distance here. That will cause the pressure to maintain its constant value. So always remember, in a piston cylinder with no friction, we always assume once the piston is moving up or down that the pressure is always constant. Back to this exercise now. The piston may be dropping while it's losing heat. So assuming that, as the question dictates, the heat is being lost and temperature originally was 400 and we are actually reaching a final of 20. So we are losing heat. Now as a result of the heat lost in an ideal gas, the pressure and volume, depending on the scenario, could be changing. Now what we know for sure that the pressure between this point and just about hitting the stops, the pressure is going to be constant. Hence, in this case, the volume will be changing. So in the first state, we know very well that the volume will be dropping down until we reach the stops. Now we have two options here. We could end up reaching the 20 degrees Celsius just before hitting the stops. Or there is a possibility that we reach the 20 degrees Celsius after hitting the stops. We don't know. Now we need to find out what is exactly happening. It's important as well to mention that when the piston reaches the stops here, the pressure here in this state will still be equal to the initial pressure of 150 kilopascal. But once the piston rests on the stops, the pressure will start to drop. So one key information that we can actually tell whether the piston had hit the stops or not is to find the pressure. If we find that the pressure is below 150 kilopascal, then we know for sure that we have hit the stops. So one way to go about this, first we can assume piston reaches the stops. This means the volume of the second state is half that of the first volume. Then we calculate P inside the cylinder. Or let's call this as P inside, or the P, or the pressure required to lift up the piston. If the pressure inside is smaller than the pressure initial, which is 150 kilopascal, implies our assumption is true. The assumption that the piston has rested on the stops is true. So using the ideal gas law, we can find P2, which is the P inside the chamber at the volume V2. Doing the ratios of the ideal gas law at the two states, we end up with this relation. Make sure your temperature is converted to Kelvin, and the pressure calculated is 130.7 kilopascal. This value is less than P1. Implies piston is resting on the stops. In state 2. However, this means that we have missed an intermediate state, the state where the piston is resting on the stops while the pressure is still 150 kilopascal. Remember, the piston is going to drop down, and just about hitting the stops, the pressure is going to be 150, and after that, the pressure is going to start dropping to the 130.7 as shown here. Let's describe what happened in a PV diagram. So we started at some point at a higher volume. We reduced the volume until we reach the stops. So this is state 1. This is state 1A. And then when the piston reaches the stops, the pressure started dropping at a constant volume. This was our pressure 1. This was our pressure 2. The question continues asking about the specific work done. We can visualize this as the area under this process here. This is the work. We know that the work between state 1 and 2 can be expressed as the constant pressure process between 1 and 1A, which is P1, V2 minus V1. We know also that the volume at the state is half that of V1, which can be equal to half mass gas constant T1 over P1. This means that the specific work is the work over mass. So taking the RT1 as common factor and dividing by the mass, so cancelling the m here, we will get cancelling the P1s, we end up with RT1 half minus 1 So the negative sign in the specific work indicates that we added work such that the process has gone from a higher volume to a smaller volume. So this is work added, and it's happening during the cooling process. So we are also losing the heat to the outside environment. If you would like to express the process that just occurred in a TV diagram or temperature volume diagram, it may look like something like this. So starting from state number 1, we know that the temperature was dropping and the volume was dropping until they reached the stop. So both the volume and the temperature were dropping, and that's why we could end up with some sort of a linear relation until reaching state 1A. Now here at 1A, where the piston reaches the stops, the volume is constant, but the temperature kept dropping. So we can express the process as such.